Hi, we are from Group 1, consisting of 4 members, Jessalynn, Nabila, Beh, and Hashir. So today, we will brief you through our CFD simulation of heat exchange equipment. So in this project, we are asked to stimulate the heat exchange equipment using COMSOL, and then we determine the heat transfer coefficient based on the temperature outlet given. And lastly, we are required to determine the flow of regime. From the question, it is given to construct a geometry with these few assumptions made. So first of all is the 2D asymmetric, non-isothermal, laminar flow, and stationary. So from this equation, RE, Reynolds number, is equal to density velocity times the length over n. You will actually get the Reynolds number to find whether the flow is laminar or turbulent. So we calculated and it is less than 2000, so it's a laminar flow. Determine the heat transfer coefficient. As you can see from the graph, it can be seen that the average heat transfer coefficient increases, the average outlet increases as well. So this is affected due to the thickness and the thermal conductivity of the medium. So larger heat transfer coefficient contributes to an easier heat transfer. And then we use trial and error method to obtain the graph of the average outlet temperature against the heat transfer coefficient. The outlet temperature given in our group is 105 degrees Celsius. The heat transfer coefficient that corresponding to this outlet temperature is actually the optimum point, which is 44.2. So the given geometry is actually depending on the heat transfer coefficient. So from X and Y, we draw out the geometry of the circle and the rectangle. So figure 1 shows the 2D asymmetric geometry, and the second figure shows the mesh. The third one shows temperature profile in 2D, and the fourth one shows temperature profile and the velocity streamline in 2D. So this one shows the type of this figure 5 and 6 shows the temperature profile revolved in 3D. The dark region in the inlet indicates that the water of the heat exchanger is at low temperature, and as the water flows from inlet to the outlet, the color changes to a lighter shade. Figure 7 shows the velocity profile. So the highest velocity is located at the red region, which is at the inlet and the outlet. This is due to the small surface area creating high velocity when water passes through it. So the middle has bright blue, which is at the midsection has high velocity as it flows through the narrow section, creating a low pressure. So as the flow area actually affects the velocity, the smaller the flow area, the higher the velocity passing through the heat exchanger. 8 shows the isosurface plot for temperature. So there is decreasing intensity of blue color shows the heat flux is increasing with the length. So the red actually shows the maximum amount of heat flux transferred within the fluid. Figure 9 shows the outlet temperature surface. So this is in terms of X and Z axis. So the outer portion shows the top view. The red region actually has the highest temperature due to the heating coil when the water passes through. So the color changes accordingly as shown until it reaches blue, which is the lowest temperature. This is because as it approaches the wall, it gets further away from the heat source. Thus, there is heat loss to the surrounding.
First, click 2D asymmetric, press next. Then click non-isothermal flow, laminar flow, press next. Press stationary and press finish. Click model 1 geometry, right click geometry and insert rectangle. insert the unit that's desired, which is 2, 0.2 and 1. Also click 4 circles that will be needed with the unit according to the group. Press the two small square that you need.
To insert all the 4 circles that's needed.
And lastly, insert the rectangle that you need in between the big rectangle. And this is the outcome for the geometry. And right click materials, open materials and insert water. Right click water and add to model. Right click non-isothermal flow, go to laminar flow and insert the inlet. Add the desired velocity, which is for our group, which is 0.09 meter per minute, and define the velocity at the point below. Then go to the temperature, the inlet temperature, and define it as 298 Kelvin. Go to study 1, solver sequence 1 and compute. Then finally, we need to determine the heat transfer coefficient. To get the heat transfer coefficient, we use the trial and error method. First, press the heat flux 1 from the non-isothermal flow and trial heat transfer coefficient value. You can put any value until you get the desired T2 value, which is for our group 105 degrees Celsius. We also define our T exit as 350 degree. Go to study 1, compute, and also then go to derived value, point evaluation 1, and press evaluate. From there, you can see from the table that we have already got our T2 value, which is 105.
Thank you for watching, and we are from Group 1.
Bye!
Thanks, sir.